Yes, hello and welcome to the KISSsys web demo where the focus today will be on the modeling part in KISSsys. My name is Cengiz Yilmaz, I'm the KISSsys product manager at KISSsoft, and I will show you first today the 3D modeling where we would like to go to the modeling part of KISSsys and how to add the elements to the model, and where you can see the new default geometry in KISSsys already when you're adding the elements there. Then the next part will be the group modeling, where we'll put two stages together. First stage will be planetary stage, and then the helical stage, which will be put together. And after these modeling tasks, we will go to the load spectrum calculation, and I will show you two options in KISSsys how to calculate with the load spectrum. And then finally we will finalize the demo with additional results, with the auxiliary results table, where we will have the system calculations and the results in the system like mass, inertia, energy, and backlash. Okay, so you have the possibility to write questions during the web demo in the question window and of the webinar tool. And my colleague Michael Schrangel, who is responsible for the development in KISSsys, will answer them live during the demo, and we will handle a couple of questions also at the end and read them aloud also for all. Okay, so now I would like to start with with the presentation. So first part is the 3D modeling, which is new in 2016 in KISSsys. Until now, we could for sure we could also create models in KISSsys until now until 15, but we didn't had any geometry, any default geometry when we added the elements to our model. So first part is here. First of all, I already started KISSsys, and I switched to the administrator mode, and I open a new instance in KISSsys. Then the first thing what you will see is that we have now the 3D viewer already here opened. So this means we will show you already the 3D geometry. And if I go to the templates, to tables, you will find under the tables here in default geometry, you will find this table new. I will copy this to my model. You don't have to copy it really always, but it's just to show you explicitly in the demonstration. So I paste it. And if I double click on this default geometry here, this is the table where you can define the default geometry of your elements. For example, of your shafts, you can define the external diameter, you can define the length of it. Then for coaxial shafts, there is also the possibility to define the internal and external diameter and the length for sure. And in case of planetary stages, we define the carrier geometry here. Then for the bearings, you can define the default type of the bearing, the distance to shaft sides here. Then for the gears, you can define the module and the width of them. Yeah. This is what we show here are all these parameters, where you will find them back when you add your elements in 3D in the model. So first, where can you activate or deactivate this functionality? If you go to System, go to the Properties window, you will find a new variable here, Default Geometry List. It's by default now in 16 is activated. This is what I would like to show you also today. And you can also deactivate this functionality if you want to work until 15 without any default geometry. This is for sure still possible, but it's a really big advantage if you activate this default geometry functionality. Okay, so I close this table. I will not change here anything. If you want to change it with a scale factor, you can also do it here with this factor. Then everything will be scaled according to your factor. And we show you also here an approximate input torque, which is possible for these dimensions here to put to your gearbox. Okay, so I close this table and I start now to build a simple two-stage helical gearbox where you can see what are the differences to the previous versions when you build the model. So I start with the element box and I will add first a gearbox group GB, and then I will add my first shaft here in 3D, so shaft 1. You find here, and this is exactly the shaft with this shaft has exactly the same dimensions which we defined before in the default geometry, like 80 millimeters of length and 20 millimeters of diameter. Then we add the couplings here, coupling for the input boundary. Then we will have two bearings on this shaft, bearing 1, bearing 2, and a gear on it, call it gear 1. Okay, and then we end the first shaft, we finish first shaft with the shaft calculation. Second shaft has to be added now once the first is finished, shaft 2, and we add the two bearings there, B3 and B4, and shaft 2 has two gears on it, gear 2 and gear 3. And we finish shaft 2 with a shaft calculation here. Then for the second stage we add the third shaft, last shaft here. We add two bearings on it and the gear and the output coupling. Okay, and we finish the last shaft also with a calculation here. So you see from the geometry point of view, we added all elements, and the main difference to the previous versions was that when I added an element, I could see it directly in 3D. This was not the case until now, so it's a very big advantage improvement for the user. So next thing is we would like to connect the gears to each other. I go to GB, and here I can find the connection elements, and I would like to create a gear pair connection. So I take this KISSsys gear pair constraint, and I say this is connection gear 1, 2. I select here gear 1 is connected with gear 2. Say OK. And I add also the respective gear pair calculation, which is responsible then for these two gears. Then what you can see now is once I created the connection, you can see how the shafts are positioned. We have the two gears in contact, and the shafts are connected correctly and positioned according to the contact of the gears here automatically. So this is a very nice thing which we have additionally, which we added also. So now when you build the model, it's not just the geometry, it's also the positioning which we do automatically. Okay, so after we created the first stage, we create also the connection of this for the second stage. So I create again a gear pair constraint, which I call gear 3, 4. Okay, I connect gear 3 with gear 4. Okay, and then you see that the last shaft is also positioned according to the contact here. And I add the referenced calculation. So this gear pair calculation is responsible to size and design these two gears here. Okay, once I added also the connections and the calculations, I can go back and add now the boundaries for the input and output conditions. So I will add them to the root directory, and here I will create first the input boundary, which is referenced or attached to the input coupling 1, and I define here an input speed of 100 RPM and an input torque of 100 Newton meters. Okay. So if input boundary is created, then the system has to have also an output. So I create here my output boundary, and I have to tell the system where the power should go out. So this will be coupling 2 on shaft 3. Okay. And now actually we finished. Also from the kinematics point of view, we defined everything in the model. One thing which what I would like to show you also is the new 3D viewer. I just added also to my model, and I close actually now the element box because I will not add any system elements additionally. For sure, when you do your own model there, you can add additional predefined tables, or you can create your own tables for output, for result values. But this is not a part of the demonstration. Okay, I close this, and if I have a look to the diagram, I will see now that the gears are connected to each other. The groups are there, but the power is not flowing at the moment, so I can just calculate first with this button the kinematics, and you see that we defined everything correctly and the power is going out from the last shaft here. Now, kinematics is done. I would like to see my elements in 3D, my gears in detail, so I can go to the settings here and change the representation mode of the elements to solid. Then I will be able to see the teeth here. Yeah. So next thing is about the positioning. Next point. As I told you, KISSsys is creating the position of the shafts automatically according to your connection, but it can be that you would like to change it, or you would like to modify or create on your own this position. So you can still always go to the shaft. When you have a normal shaft model, you can always go to the shaft and click with the right mouse button there and go to dialog to check the actual positioning, which is done from KISSsys. Or you can always go to reset position to reset it and to set it on your own manually. So you can go to reset, and then you can select own input if you want. Own input means you have the option to define the position through the Cartesian coordinates x, y, z of this shaft in the global system. Or if you want to position it according to the gear pair calculation, you can again go to reset position and select according to calculation and select the respective calculation, which is the first one here in this case for this position of shaft 2. And then you have the same dialog. So you see that KISSsys created you the position according to the calculations before automatically, but you can always do it on your own also with the reset position function. What is also new in 16 is, for example, if I go to shaft 3, go to dialog, I see the positioning, and now I have an option. I can change the direction of the shaft. I can select reversed, and then the shaft will be just mirrored or reversed in 3D here. Yeah. So these points about the positioning. The rest, everything is still the same like before, but a couple of changes just to let you know, which can be important when you create your model. So I create the model now. Next part would be to size the gears. So I can go to the gear pair calculation, go to gear sizing, and select the ratio. Let's say I have a ratio of 4 and the pressure angle of 20 degrees and helix angle. I don't change it here. Then KISSsys will size the gears automatically according to the required safeties. So it will have the input torque in the background, and it will take the required safeties and size them accordingly. Okay, first stage is sized, then I can go to the second stage and size it in the same way. And when I put the ratio here, let's say 3, and then we can find the second stage also sized in 3D. And what we can see here is now that some bearings are inside of the gear 3 here. So we can change the position of the bearings to have a better design, and then we can size the shafts in a second step. So maybe we can go here to the shaft calculation, and I can make the the forces and the elements movable, and then with this arrangement should be fine. And now I would like to size the shafts directly without going to KISSsoft. Staying in KISSsys, I can just go to shaft 1 calc and do a right mouse click and go to shaft sizing and bearing selection. And here you can define the bearing lifetime, required lifetime, which is taken into account when they are sized. And we can define if you want to use the own bearing definitions or the definitions just defined here in this list. And adapt shaft to bearing means that we adapt the shaft diameter to the inner diameter of the bearing when the bearing is bigger than the shaft while we try to size it. Okay, and then the first shaft will be sized accordingly, you see, and in the same way I can do it for shaft 2 and shaft 3. Go here to the calculation, gear sizing, shaft sizing and bearing selection, and they will be sized. I go to shaft 3 and use the same functionality, I don't change it here, and we will find back the shaft and the bearing diameters here in 3D. So if you see now, okay, this shaft is a bit too short, maybe we can go again to the shaft calculation and adapt there the arrangement of the bearings according, or we can change the cylinders and so on. So these are just some modifications here. Okay, so that's it actually for my two-stage model. And what I can show you also is the new viewer here. So we can rotate it here for sure in the old viewer. If I go to play button, I can rotate this system. But we have now in 16 also a new viewer. If I double click on it, then we'll find back another view of the gearbox, and we have here also the option to rotate and also some options to show the deformation in radial and axial direction. So radial deformation, we can size it and scale it and then to see it in 3D also. Axial, we don't have any axial forces, so I will not change it. And then we have also the option to create some cross sections in different planes. So this is a new viewer where we add additional functionalities still. So the goal is that we have it in 17 then fully. Yeah. Okay, so I will close this, and this was the first part of my demo, the two-stage helical gearbox. I will save this file because we will use it later for the load spectrum calculation. Just save it here in the web demo as two-stage gearbox. Okay. So I will open then a new KISSsys instance, and now the second part is the modeling of the planetary stage, and here I do the same steps. So we will not change the default geometry table, I will use the same dimensions, and here I can start with the element box and create the group GB, and the goal is here that you see also a model where you have coaxial shafts, and in this case in the planetary stage we have the sun ring and the carrier shaft coaxial to each other. So I will start with the coaxial shaft element here, and the first one is the sun shaft, and you will find it here as well in 3D now as it was before. And sun shaft has a coupling, I call it coupling sun. Then it has, let's say, two supports and the gear called sun gear. And that's it actually for the sun shaft. And second shaft is the ring shaft, which is also coaxial, so that's why I created here with the coaxial element, ring shaft. And you see it also automatically, it's positioned the same coaxial to the first shaft in 3D. And this has the ring gear on it. And then the support to have it supported in 3D in the space, and we will add a coupling to fix the rotation around his own axis, so with the boundary condition. So that's why I will add here a coupling ring. And actually that's it for the ring shaft. The third shaft is the carrier shaft, which is also coaxial to the others, and you will find them also here back in 3D. And first we say there are two bearings on the carrier shaft, which is also our output shaft. And we will have a coupling for the output. This is my coupling carrier for the output of the system. And now you will see the difference. Once I add this element, this special coupling, which is representing the planet carrier wall, let's say, the connection to the pin here, we will see that the carrier is transformed. This shaft will be transformed to a bigger. Will have a bigger diameter, which is representing the carrier automatically. So here now I will add this special coupling, carrier element. Okay, and then you see that the carrier is getting bigger automatically because it knows now that it's the carrier of this system, thanks to this element here. Then next thing is the planet group, which has to be separated inside of the carrier. So group planet, and we have the planet pin and the planet gear body there. So first one is the pin shaft, which is coaxial to the planet gear body. On the pin shaft, let's say we have two supports, support 4 and support 5. And in the planet group we have the planet gear body as a coaxial shaft, and we have there the planet gear itself. Okay. And to fix the planet gear body, actually we add also support there. Okay. And then in general, in most of the designs, since this is rotating on top of this inner shaft, so we have to have connection roller bearings here. So we add them to the planet group, and the connection roller bearings can be found here. So this is CB1, where we select the inner shaft and the outer shaft, and CB2 in the same way, pin shaft, planet gear body as an outer race. Okay, so we have all elements actually now from the geometric point of view. Now we just have to create the connections that the kinematic can be calculated in the system. And first I will create the sun planet mesh and then the planet ring mesh. Let's go to GB and go to here to the connections, to the KISSsys constraints. And we have here, before we use the gear pair constraint, since this is a planetary system, we have to use the KISSsys planetary gear pair constraint. And here I create the sun planet constraint first. Configuration is sun planet. Then here I have the sun gear as the first gear, the second gear is the planet gear, and the carrier element is this special coupling. This information is needed because here we know then how many planets are attached. This is saved in this special element here. Okay, and now you see how it is transformed. So I have the mesh between sun and the planet. And then the next step is the mesh between the planet and the ring. We change the configuration to planet ring. Gear 1 is my planet gear, gear 2 is my ring gear this time, and I have to select the correct carrier element here. Okay, and then once we create this, you see that we have already the planetary stage correctly positioned. All elements are, all groups are correctly positioned in 3D, and you can check the contacts. Now, next thing would be to create all calculations. I would like to start with the gear calculation, or the planetary stage calculation, which is here, this one. I can add it to GB, and I just call it planetary calc, planetary gear calc. Okay, and we select with the type of our connections which we use. We use the gear pair constraints. Sun planet was this one, and planet ring mesh is this one which we created before. Okay. Then next thing is to add the shaft calculations. So I can go back and I can add first, to have the shaft calculations of this coaxial shaft group, I have to add it here into this level. So the coaxial shaft icon is here, and I call it mainline calc. So this shaft calculation will take all 3 shafts into it, so it will take them in his calculation. And we have another shaft group in the planet itself. That's why we separated this from the others. And these 2 coaxial shaft group has to be also used from this shaft calculation. I call it planet calc, and this planet calc will take both shafts into it. So as a summary, we have 2 coaxial shaft calculations and 1 gear calculation in our model. Okay, so after I added the calculation, I would like to have first the kinematics working in KISSsys. So I can go to the root directory and add the boundary conditions. First one to the sun. This is attached to the sun coupling, and we enter some input speed and input torque there. And I add a boundary for the ring, which is attached to coupling ring and not constrained, just constrained in the speed, means that we fix it here with a 0 speed. This is very important for the kinematics. Okay, and then the system has to know where the power goes out, so I call this boundary carrier, and it's attached to the coupling carrier, and this is not constrained, so we can just click on OK. So I close the element box now because it should be fine at the moment, and I will have a look to my system here in 2D. So I can see that it's going from the sun through the planet and the ring system out from the carrier. So it's not going out at the moment. Actually, it's just connected. But to have the kinematics calculated, I can just click on this button, and we see that the power is going out in from the sun and going out from the carrier here. Okay, so this is our default geometry for the planetary stage, and it can be that now you have a different design for sure in your application, and now you just have to go to the specific shaft calculation. Let's say the main line here is different, and you can go to the main line calculation and you can change your dimensions, or you can change your length of some cylinders here. I will just do it for this sun shaft because this is created automatically very long, because we add it always when we add a coaxial shaft, it's increasing this length. So this is something which we do automatically with this 3D modeling. And let's change here this length to 60, and maybe this bore here we can delete. Don't need it, and it can be that the output from the carrier is not just from this from these parts. That can be that we would like to have another cylinder, so you can just right mouse click here and add a new cylinder and change here maybe also the diameter depending on the request and the length 60 or 80. Yeah. So this was the coupling of the sun. It can be put on the left side, and then these two bearings we can put them on the additional cylinder which we created like this. This is the second support of the sun shaft here. So yeah. So you see that you can really change the geometry according to your application easily after you have a default geometry. And let's change also this effective diameter of this coupling to 170. Let's say that it looks better in 3D. And here we have this support on the ring where we didn't fix the rotation around y-axis because it's already fixed in the kinematic calculation with the boundaries in KISSsys. But since it's just one support here, we also have to fix the rotation, otherwise the shaft calculation will not converge. The rotation around x and z direction. Yeah, and then shaft calculation is converging. So this is just an example how it could be modified. Okay, then I make a refresh and we see now here that the arrangement has changed and according to our modification in the shaft files. So now you can go also to the planetary calculation, change the bearing. So all these modifications can be done step by step, but this is the idea, is just to show you an overview what is possible. Okay, so now you could see now two different models. So first one was the two-stage helical gearbox. The second one was the planetary stage, which is more a coaxial shaft model, let's say. And you know, in the first first gearbox, we positioned the shafts with the normal by clicking with a right mouse click on a normal shaft. And here, since you have coaxial groups, you have to click always on the groups with a right mouse click and change or have a look to the position. In this case, it's the planet here, which is positioned directly from KISSsys. And if you make a right mouse click and go to dialog, you can find back the position, which is also done according to the calculation from KISSsys, but you can always go here and reset the position and set it by own input, or again do it according to calculation and select the planetary calculation. You will find back the same window which KISSsys created for you. Yeah. So this is how it is done. Actually, the 0 point for the position in this case is GB, which is here at 0, and this is defined as own input. So you see, if you have own input, you can select here in Cartesian coordinates the position. Okay, so now you could see two basic examples where the 3D modeling was showed. And I would like to go to the next part, to the group modeling, which is also a new feature in 2016 in KISSsys. And so I don't save this model, just open a new instance. And couple of points to the group modeling. Group modeling can be used if you have to put predefined stages together, so to merge them together. So for example, here in the group box here we already defined some stages. We have the one stage model, we have the planetary stage here, and some 3 gear calculations stage, some bevel stage, worm stage, and so on. These are already here in the installation, but for sure you as a customer, you can also create your own stages and save them as templates and load them then again from the user templates here in your model and merge them according to the instruction, which I will also show you now. Okay, so the goal is that we first add a planetary stage here from the default templates. Let's say this is my stage 1. And you can see it in 3D here. And then I would like to merge this with a helical stage, one stage helical gearbox. So here I just add it and I say this is my stage 2. And I close this window. Now I can see both stages in 3D, but they are not attached or connected to each other. And my goal is now to have the carrier shaft here as the input shaft of the second stage. So what I do is for the coaxial, in case of if I want to merge a coaxial shaft with a normal shaft, I have to click to the coaxial shaft, to my carrier shaft, and go to the function merge. This is new in 16. And we say, okay, on the right hand side, I would like to add shaft 1 of stage 2. I click on OK, and then you see that it's attached here on the carrier, and you will also see that this is now one shaft with the carrier. So it's not a separate shaft here, and we can check it very nicely if you go to the shaft calculation here with a double click. You will find here that we added this cylinder to the carrier shaft, but it's still the carrier shaft itself. If I click on the carrier shaft, you see everything is getting red. Okay, so maybe it can be that you don't need this cylinder anymore. This is just one modification which you could do. You can delete this cylinder here, for example, and delete also this bore. This is just a bore which is still from the previous shaft here. You can also delete this, and you can increase the length of this cylinder and decrease the diameter accordingly that it fits to the gear, and you can just modify the position. If you need to delete one bearing, can be also done for sure. Just this has to be done from KISSsys in order to override KISSsoft, because if we delete it here, it will be all written from KISSsys again. So this bearing has to be deleted from KISSsys if you don't need it. So this is just one possibility what could be done. And then if I refresh, then you will find back here this as just one shaft, one cylinder, and it's continuing to the second stage here. So very fast method to model, to couple multiple stages to each other. And these standard stages could be also your own stages. So you can create first your own stages and then put them together according to the instruction which I showed you. Now, next thing to finish this model is you remember, you can recognize maybe that we don't have any couplings on these shafts because we would like to give this freedom to the customer that he can add his input and output couplings when he finished his merging functionalities. So let's say we go to the sun shaft. I finished already and this is my input, so that's why I add my coupling here, coupling sun. And on shaft 2 there will be my output and I add my output coupling 2. Okay, and I go to the root directory and define now the input and output boundaries. So the input boundary is attached to the coupling sun, where I define some input parameters, input speed and input torque. And I also define the output of my system, which is attached to coupling 2 on shaft 2. Okay, and then actually I am finished now, and we can just calculate the kinematics of it, and we can see that it's going through here, and I can activate the solid view of that system here and also rotate it. So this was a simple example how to put two groups together and how to merge them, that it's creating, it's merging as a one shaft, it's not coupling with two different shafts, which was until now also possible, but you had to add couplings and connect them through coupling connections, but now it's really getting one shaft. Okay, so this was the third example I wanted to show you, and now I would like to switch to the system calculation, to the load spectrum calculation. So as a summary, you could see the 3D modeling and the group modeling now. And let's take the first mod which we created and do some system calculations, some load spectrum calculations there. For this, I will not save this one. I will just open a new model, and this one is the one which we created just before together. And if I open the 3D viewer, you will recognize it again. And now what we do, what I would like to show you is the two possibilities which you have to calculate the load spectrum. One is through the load spectrum from the database of KISSsoft, and one is with the calculation with the load spectrum template from KISSsys. So the first option is, if you click here on this button, you already have access to the load spectrum database, and you can select one of these load spectras which are already in the database of KISSsoft. And for sure you have to first define this load spectrum in the database, and this can be done in every KISSsoft calculation. So let's go to the KISSsoft gear pair calculation here and open the database tool here. Now is write protected because I didn't start the software with administrator rights. But if you start with administrator rights, then you are it's also possible you have the rights to create a new spectrum there. But I would like to show you where you can find it. Here it's the load spectra database. If I display this, I will find back the same table which I showed you before in KISSsys. And here you can also use this basic file. I can display this, and you can have a look to this duty cycle .dot file, which is saved in the .dot folder in my installation, and you can find back this is the duration, then the torque and speed factors here. And you could modify this file, just overwrite it, and then you will have this as a selection which you saved, or you can also create here a new load spectra. Okay, so this is just where to find or where to create your spectrum, and then let's close this. Let's close KISSsoft again and select here with this icon one of these options. I would like to use this basic file, and here I would like to calculate the full load spectrum and also show the report at the end, and I would like to run the calculation immediately if I press OK. This is just a message, and then here you can find back your spectrum which you defined in the database, and the calculation is going through. So what is done now is this spectrum is transferred to all gear and to our shaft calculations, and we will find back the results in the KISSsoft report. So you can see here that the same is considered, the same spectrum which was also defined or selected from the database. So this is now the gear pair calculation first, and if you go down you will also find the same for the shaft calculations here for each load element on the shaft. So this is the first option, and we don't have any additional results. You can check the results just in KISSsoft in the KISSsoft report. Okay, so you can find, for example, for the gears, if you go down, you will find the results immediately here, the safeties, and if you go down to part 10, you will find here the required safeties and the tools routes, the service lives for root and flank, and the damage is also in this table. In this case, we don't have any damage, that's why everything is 0. So this is how you could check the results from the calculation from the database. Now I would like to show you another option, which is where you have more freedom and which is also which we can suggest also for complex models where you have more boundaries than just one input, one output boundary. This is the method with the calculation with the load spectrum template. For this, you can add first the load spectrum template from the standard default templates here, just to your model, and you can do a right mouse click and go to definition dialog first. And here, let's say we would like to define just spectrum with 3 bins, and my frequency type should be in fraction, and the required lifetime is 20,000 hours. And my values here, you can also define it as absolute values, not just as factors. And the speed is defined at the input, and the torque is also defined at the input. If you select factors here, then you have to define your reference speed and reference torque. But we would like to use the values. And if you have a shifting gearbox, a transmission gearbox, then you can use the speed table in cooperation with the load spectrum template. And if you would like to define additional parameters, for example, you would like to define the force for each pin, then you can create here additional columns where you give the force, the amount of the force here for each pin there. So I would like to take these settings, okay, and then here you can define your own spectrum for the system. Let's say I have 30%, first pin 50%, and 20%. So this should be 1 equal 1 here in that case. And the torque was 100. Let's say it's going down and going up to 120. And speed was 100 and just going down to 8. So like this. Okay, this is just my example spectrum. And now for the calculation with this spectrum, I can just click on this button in that case. And here I have different calculation options, from just calculating a single bin from the spectrum until calculate all bins, the full load spectrum with the intermediate results, and exporting also the KISSsoft files. And I would like to use the last option here because we can have a look then to the KISSsoft files once the calculation is finished. And then here I would like to open the KISSsoft report, and here we have new options now in 16 that you can consider the efficiency template, so you can consider the efficiency calculation for each load bin now here. So you have to add first your efficiency template in your model and then define your parameters there and then combine it with the load spectrum calculation here. And we can also calculate with the housing stiffness, and there we calculate for each bin the bearing offsets. Okay, and then the calculation starts, and we have the progress bar here which shows at which bin KISSsys is doing the calculation at the moment, and then finally we have to generate the summary calculation, then doing some post-processing, and then the KISSsoft report is popping up, and we attached all reports in the system in this file, so you can find back again. This is now the gear pair calculation, gear 1, 2, and you can find here exactly the parameter which we defined for speed. Here 190, 80 and 190, 120 for the torque. So this is really transfers to each KISSsoft calculation. Here it's just a gear pair. And in the same way we can find the safeties, and also if you go down to part 10, we can find the service life, the system service life, and the service life for root and flank for the tools here. And we can also find back the damages here in the KISSsoft report. Yeah. So damages are calculated on the basis of the required service life, on the basis of system service life, and on the basis of the individual service lives here. So this is one option how you could check the results of your system. But another nice feature for the calculation with the load spectrum template is if you go to your project folder, you will find back this folder which we created from the load spectrum calculation, and in this calculation, in this folder, we can find the different KISSsoft reports again. This is the report which I showed you before, and additionally we are writing out the results CSV file and the damage CSV file. In the results CSV file, if you open this one, you can find in an overview first the gear calculations, and then we can find there the safeties and the lifetime for all gear calculation, and calculate for each bin and for the total load spectrum calculation here. And we can also see for the bearings the lifetime and the forces for each bin. And if you go down to the shafts, if you define some cross sections, you will find the dynamic and static safeties for at these positions for this shaft. And nice thing is also we show at the end of the file the weakest components in your system and the utilization. So we can see now gear 1, 2 is used more than 100%. So we have to check this gear pair calculation there. So yeah, this is also what we can see here, that with these 9,000 hours, it's less than all other components. Okay, so this is one way to check the results, where we check the safeties and the lifetimes. And then to check the damages, we create another damage CSV file where we show again, as it was in KISSsoft, we show the damages calculated based on the required lifetime and damage case calculated based on the calculated lifetime. For sure here it's always 100% at the end, and here depends on how much the calculated lifetime is. So we give out the damages for the gears and we give out the damages for all bearings here in percentage. Yeah. Okay. Then the last point for regarding the load spectrum calculation are the one of the main advantages are that we write out the single calculations here. So for example, if you have 500, 1000 bins, this can happen sometimes in different applications. You need to calculate with a lot of load bins. Then you can just export these files as we did together, and then you can open the exported file. For example, for the gear pair calculation, you can open this one, and if you go to rating, you will find back the load spectrum here in this file and the reference data also. And now if I calculate, this will calculate with the whole spectrum, but the nice thing is also, if you don't know in which bin, for which bin you have some problems or some inconsistencies, you can just go here, consider only one bin in the load spectrum, select this option, and then change the bin, and then check why it's giving an inconsistency and why it's not converging, for example. Especially for the shaft calculations is can be very helpful because in some cases shaft calculation is not converging with in some load bins, and this can be also checked in the same way. If you open the exported shaft file, go to basic data, you can also say here consider only one bin of the spectrum, and then you can switch between the different spectra. And you can also find back the spectrum in each force element in the shaft. If you go here and click on this plus button, you will find back the load spectrum for each load element. So this is really a nice, helpful function if you have some convergence problems during the load spectrum calculation, especially if the spectrum is very big. Okay, so this was the calculation of the load spectrum, the two different possibilities which you have. And as a last point of our analysis of our gearbox, I would like to also check, for example, the system results. So for this, I add this auxiliary results table to my model, and I calculate here these parameters, and we will find back some system results like masses, mass for gears, for bearings, shafts. If you have a casing, then you will also find back the casing mass, and the inertia of our system, the kinetic energy, and the backlash. And depending on your reference boundary, backlash will be different. This is now when you rotate the input shaft, you have this amount of backlash, minimum and maximum. And if you change here and calculate again, change the reference boundary, then will be different for sure. Yeah. So, and like this, you can analyze the whole system. So first you design, depending on if you have already defined some stages, you can combine them, or if you have completely a complex system, you can start from scratch and model with the help of the 3D modeling in KISSsys. And once you create your model, you can calculate with a load spectrum if it's needed. You can check the results, you can check the safeties, the lifetimes of your elements, and check the system results here. And if you have to optimize some of these parameters, then you go specifically into these elements and modify there and check again the results until you have the optimal solution. So this was just to show you in around 1 hour the new features in KISSsys about the modeling and some system calculations. Now I would like to go to the questions. I would like to switch to questions and just read some important questions aloud. In the model creation, why does the position of the bearing not change in the diagram? Also, we changed its position and it is also changed in the 3D model. Okay, yeah. In the diagram, so it should be changed when you change it in the shaft calculation, then it should be automatically arranged.
Yeah, the X and Y coordinates are a 2D diagram. And so if you change it, it is shown also in the 3D model and the 3D viewer, but in the 2D diagram, there's just shown whether there's the flow of the power and the schema of the whole model. So if you change the positions of, for example, this gear on the second shaft, then it is not shown in this schema. It's just shown in the 3D.
Yes, this is an answer from our development. And yes, where is the critical speed mentioned in the report? The critical speed, this you have to check in KISSsoft. Actually, yeah, for this topic we can send you an email directly, because this is more a KISSsoft relevant topic. Then can the model developed in KISSsys be imported to AutoCAD? Yes, this for sure. You can export this 3D viewer with a right mouse click on the 3D viewer and go to export geometry, and then this can be exported here as a step file, and then you can open it in every CAD software. Okay, so there are no other big or issues or questions which I can see now from the chat from my colleague. Yes, so I would say, yeah, so thank you very much finally for attending to the web demo. And yeah, if you have for sure additional questions, you can write an email to info@kisssoft.ag. If you have questions, technical questions, you can write to support@kisssoft.ag. And for sure, in future, we will have additional web tunnels for KISSsys. So keep checking our website, and not to forget that there will take place also KISSsys basic training here in Bubicon in end of August. So information about the schedule can be found on our homepage or in the handout, which you can download as a PDF from the webinar tool. So finally, I wish all of you a nice day or evening, depending where you are. So, and I hope to meet you next time.